Okay, as I said, first part was the formalism, showing you really this stochastic thermodynamic theory and its latest developments. Now we turn to the application part where we will look at energy conversion. We will look at, since we have now a description that connects with thermodynamics, but we have time scales in addition, we will be able to study a lot of interesting questions concerning efficiency of transformation in finite time. And I will start and probably stay, this depends on the time we will have, on autonomous devices. So autonomous devices means I don't have an external explicit time dependence. And I would like to make a comment because somebody asked the question. I want to make sure that everybody understood what I meant by external time dependence. I had two different ways of driving my system out of equilibrium. Having two reservoirs at different temperature or a time-dependent driving force, as I said. This time-dependent driving force, in principle, has nothing to do with the reservoir. You can think of it as, for example, an electric field that acts on these energy levels of your system. Okay? So it is not a bath property. It could be. I could make temperatures time dependent. The formalism still hold. But to make it simple, the simpler picture is you have an electric field, and by changing the value of this electric field, you can tune the energies of your levels. Okay? So these are two different mechanisms. One is the bath. The other one is really acting on the energy levels of your system. And this is why it's related to the work also, because it's really an external force. This was a clarification. So here, we will not have this time-dependent external force. We will only look at devices that operate in steady state. And maybe if we have time, we'll look at non-autonomous devices. Now, the formalism, I will have to extend it a little bit to start, because in the application, I want to speak about thermoelectricity and photoelectric effect. So I need to incorporate now also matter transfer. Before, we considered what we call in thermodynamics closed system, which means they are exchanging energy but no particles. Now we will consider open system that exchange energy as well as particles. The description is very similar. We again have the stochastic master equation, okay? But the local detail balance now is a little bit different. Yeah, I should say, of course, that to each of the level m now of the system, these abstract indices, I associate not only energy, but also a number of particles, okay? So each index m has a certain number of particles. So whenever I have a jump between one level and another, I have an associated change of energy and an associated change in the number of particles. So my local detail balance condition now is extended. Before we only had this contribution, okay? The temperature is here. Now we have this additional contribution here with the chemical potential of the reservoir. In the case where the two chemical potential of the bath are the same and where the two temperatures are the same, you can show that this leads to the grand canonical distribution. Before we had the equilibrium distribution that was the canonical one. Now we need the grand canonical one. And indeed, this local detail balance gives us this grand canonical distribution. So with this new modified, extended local detail balance condition and this stochastic rate equation, we will again construct the thermodynamics. And it works exactly in the same way. The mathematical formulas are the same. So the heat flow will look like that. This was the same as the one I showed you before. But since now the local detail balance is different and contains this particle part, the heat now contains two contributions. Not only the energy flux associated to the reservoir nu, but also a matter flux. Because in this ratio, we will get, if we take log of this, we will get this guy here, mu times the difference in n. And this is, I hope you see them here below, the definition. So I average over all the jumps, the changes in energy. This is the energy current. And here, I average over all transitions the change in the number of particles. So this is the particle flux associated with the reservoir nu. Okay, so the definition of heat now contains two parts, not only energy flux, but also matter flux, multiplied by chemical potential. This is the consequence of this. I will tell you why I only show you the entropy flow. I should do this in order, but okay, I'll come back to this in just a second. So, as I said, we will look at devices operating in steady states. This means P dot is equal to 0. In the steady states, this mathematically you can show it, but physically it perfectly makes sense. The current, the matter current entering from one side will be minus the matter current entering from the other side, because your system doesn't change. So if you look at the number of particles in your system, in average it doesn't change. It means that all the fluxes have to sum up to 0. Same thing for the energy. If you sum up all the energy fluxes, you have to get 0. So if you have only two baths, the energy or matter flux from the right reservoir is always minus the energy of matter flux from the left reservoir, and we will choose the right one as the reference. Else it's redundant to keep these indexes. We have this extended notion of heat. So now work per unit time, which I will call power, and I will put a minus because usually power is what you can extract. I define work as the amount, so work is positive when the energy of your system increases. So power is what you extract, so you put a minus sign because it's what you want to get out of your system. So because we are at steady state and energy is conserved in the steady state, the energy of your system, the sum of the heat is minus the work, because energy is work plus all the heats. And since energy is 0, you put work on the other side, you get that minus the work is the sum of the energy. And as a result, you get power. If you plug the expression I showed you before here, so the explicit expression of the heat with this conservation law, you will find that work now is given by the current, the matter current, times the difference in chemical potential. What does it mean? It means this is the energy required to bring particles from one lead to the other. Okay? The matter current is the number of particles crossing your system per unit time, and going from one to the other chemical potential is the relevant quantity associated to work. What we will be doing, we will be interested in thermoelectric effect, which is how can we use a thermal gradient, a difference in temperature, in order to bring electrons from lower to higher chemical potential. Okay? And so the work output that we are interested in is precisely this quantity, because we want to pump these particles up in chemical potential. I should insist on the conventions. So we will always take the right temperature, which is the hot one. And since we will look at thermoelectric effect, we will always assume that the right chemical potential is lower than the left one. Okay? So in principle, heat will flow from the hot to the cold, And if there was no heat gradient, particle would like to flow in this direction, from higher to lower chemical potential. But what we will do is we will use this difference in temperature to pump particles from here to here. And the work will be given as the number of particles crossing the system times this difference in chemical potential here, okay? So we have our definition of work in this context. Now, I said I only showed you heat flow because now, since I'm at steady state, S dot as energy or as number of particles is 0 because it's a state function. It only depends on P. So obviously, if P doesn't depend on time, S dot is 0. So S dot was, you remember, we split it as S flow plus entropy production. So because this is 0, we have that minus the flow is the entropy production. And so this quantity is also, I didn't write it explicitly here, but it's always positive. And this I showed you on the last slide that it had this structure. Here I replaced heat explicitly by its form. Okay, now this I can rewrite in the following appealing way for people who are a little bit familiar with non-equilibrium thermodynamics. So entropy production has this flux force structure. So this is the thermodynamic force associated to energy, and this is the inverse temperature difference. And this is the force associated to matter transfer, and it's this difference in the mu chemical potential divided by temperature of the two reservoirs. So this is what we are familiar with. Again, it's nice to see that this formalism leads to all the things we are familiar with in thermodynamics. So we have this flux force relationship. It will be crucial in a way in the future to realize that the current is always a function of these forces. And so linear term, you might have heard about linear theory of irreversible processes. It's when we expand this current in the linear term of these forces, okay? But this is a general expression. Sometimes there is confusion on that. This is a general expression, but if you assume that your current here, your two currents are linear functions of the forces, you can expand this to linear order, then you get a linear irreversible thermodynamic form for this entropy production. I will show you this later. Okay, so as I said, what we want is to extract work, and this work was pumping electron up in chemical potential. And using the thermal gradient, so this is a thermal machine in the standard Carnot sense. So the efficiency associated to this process is defined as the Carnot efficiency minus the work per unit time divided by the heat coming from the hot reservoir. Since the hot reservoir was the right reservoir, it's work divided by QR. And this is a way to rewrite the entropy production. It's simply a little bit of algebra to use the formula from next slide and rewrite it like that. We can, using this, we can rewrite the efficiency like that, where we explicitly have here the Carnot efficiency plus minus a term that contains the entropy production, and the heat from the hot reservoir will always be positive because that's where the energy comes from. So you see, this is always positive. This is always positive. So what we see is that we can only be below or equal to Carnot efficiency in the regime where we are, of course, using a thermal gradient to pump electron upwards. We always consider that this is the regime in which we are. So this shows us that the worst efficiency we can get is 0 when entropy production, when this ratio is very high. And the optimal that we can get is actually when SI dot is 0, which means in the reversible case, we've seen that entropy production was related to being 0 was related to the fact that we are at equilibrium. So it's only when we are at equilibrium that this term is 0 and that the efficiency becomes equal to the Carnot efficiency. Okay, so this quantity eta, the efficiency is always between these two bounds. And the upper bounds is only reached at equilibrium. In the last slide, I wrote entropy production as the sum of these two contributions. If this is 0 at equilibrium, it means that we have this relationship. And this is a generic statement. I will show on the next slide. It's not always the case, but generically it is the case. How can you have this relation satisfied? As I said, the current is a function of the two forces. So this and this current are functions of these two forces. So generically, to have this relation satisfied, you have to put the two forces to 0 to be at equilibrium. Mean temperature gradient to 0, chemical potential gradient to 0. Okay? And this means that your Carnot efficiency, which is related to this ratio of the temperature, will also go to 0. And power which on the last slide was related, was proportional to the current at equilibrium also goes to 0, so power also goes to 0. So in a sense, what I'm saying is that when you operate close to equilibrium, to reach the best efficiency, you have to operate close to equilibrium. And generically, to do that, you have to put all the gradients almost 0. But in that case, Carnot efficiency becomes 0 and power goes to 0. Okay? So it's not what we would like to do, because we would like to have a strong power output, generate a flux, use this thermal gradient to generate a lot of power, electrons going up in chemical potential. And so we have to face this problem and go out of equilibrium and see how we can get higher efficiency. Now, this is an important point. I said generically. I will show you now that this is not always the case. There is a particular situation where this is not the case. And this is the tight coupling condition. This is a crucial notion to reach high efficiency at equilibrium as well as far from equilibrium. There might be exceptional situations, and we will discuss this on the specific model I will consider, where the energy current is proportional to the matter current. Okay? Now take it as a mathematical assumption. I will show you later how this can physically occur. But typically, it's when the elementary processes carrying heat energy are also the same that carry the change in particle. So when the particle itself is the carrier of the energy. It's a little bit vague. You will see what it means soon. So what happens if we have this strange condition here? This was our form for the entropy production. If we use this, we see that we have something appearing here. I define I as this. This is a convention. So I can write now my entropy production as a single force time flux relation, where this effective force is a sum with this constant here of the two gradients. Now, what will be very specific here, but okay, I said it later. Let's, okay, this is the first thing, this collapse of the force. Let's look now at the efficiency. This was the form of the efficiency that we had. I plug this here. Another strange feature of this tight coupling, yes, is that this quantity doesn't depend on the flux itself anymore. This is another curious characteristic. efficiency itself is independent of this flux now. Because of this assumption, we get this strange property that current is never explicitly present here. You see, I have the force, the temperature, Carnot efficiency, but current is not explicitly there. Now, how do I reach Carnot efficiency? Again, when entropy production is 0. But now entropy production can be 0 when this global F is 0. And it doesn't require anymore the 2F separately to be 0. So this is what I was referring to before. We have this curious property that we can have a matter curve, the force associated to matter, which is related to the potential gradient, chemical potential gradient, which is non-zero, and the thermal gradient, which is non-zero, and still have this effective force 0, and therefore the entropy production 0. Okay, so this is remarkable in a sense. You can have two gradients, but because you have this collapse, you are still at equilibrium. Entropy production is 0. Detail balance, detail balance is satisfied, but you have two different gradients. However, you still have that power goes to 0. What did I do? Yes. You still have that power goes to 0. So equilibrium, we still want to go beyond equilibrium. Here, we still have the problem that close to equilibrium where we can reach Carnot efficiency, we have a 0 output. So we will now move to the non-equilibrium aspect of the problem. But I wanted to introduce this tight coupling condition because it will be very important for efficiency out of equilibrium. And you've seen there is this very strange property that you can be at equilibrium with two gradients that are non-zero. Okay, now we move to the out of equilibrium. We'll start to look at the efficiency out of equilibrium. And in the regime which is of most interest for practical application, it's the regime of maximum power. So what we will do is we will ask, okay, I want a maximum power output. This means I will be out of equilibrium. How efficient will be my process at this value of the maximum power? And as a first step, because this is where we can do all the analytics in a general way, but limited, it's close to equilibrium in this linear response regime. As I said before, linear response means that these currents that are functions of the forces, I will expand them in terms of these forces to the linear order. Okay, this is a linear. Of course, I have nonlinear contributions here in general. A system will always have higher order contribution, but we neglect them. We say that we restrict ourselves to reasonably close to equilibrium situations. And we do this expansion here. It follows from the positivity of entropy production that these coefficients are always positive, and this is called the determinant of the Onsager matrix because these are the Onsager coefficients. When you expand these two fluxes in terms of the forces, you get a matrix of coefficient. It's called the Onsager matrix. And this is the determinant of this Onsager matrix. In the tight coupling case that I mentioned before, of where these two currents are proportional, we exactly have that this determinant is 0. That's another, it will be an interesting limiting case. Okay, now we do this expansion and we simply put this in the expression of the currents that we had before. So this is simply a way to rewrite. I should actually, I put the index R here, but it's not needed because, as I said, I use always R as the reference. So this is an explicit form. I rewrite this in an explicit form where I put the Carnot efficiency explicitly here, which is related to the thermal gradient and the difference in chemical potential. So this is related to this other force, the matter force. I wanted to put them more explicitly for this calculation. That's a choice. Then I put these two currents, so this is simply a way to rewrite this, okay? And I put this in my expression for the power that I had on the previous slide. Now, this is, so to remind you, where did I put power? Okay, power was here, okay? So I replace this current here by this. And now, for a given value of the thermal gradient, which is here eta Carnot, because Carnot is a function of the difference of a ratio of two temperatures related to the gradient. For a fixed value of this, I will maximize power with respect to the difference in chemical potential. So what I'm saying is I fix my difference in temperature, and I say, when do I get a maximum power by changing the value of my difference in chemical potential? Okay, I'm looking for the maximum in difference of chemical potential in the power. If I do that, this you can, it's a little bit of algebra. It's not complicated. You can really do it at home. It leads to this condition. We find that the maximum of this power, and it's crucial, you can show it's really a maximum because you take derivative of power with respect to delta mu is equal to 0. You find this condition. You can take the second derivative, and using this property, you will show that it's indeed a maximum. So now that you have this value of the maximum, you can show that the ratio of this current takes this form. And this ratio of the current was appearing in the general expression for the efficiency. I didn't write it explicitly. Sorry. If you plug here, if you express this in terms of the currents, okay, you have to believe me now. I realize it was there actually, but I canceled it. The efficiency depends only on this ratio, okay? So once I have this value of the ratio, I can plug this in the efficiency, and I can show that my efficiency at maximum power, because I use this condition here, is given by this expression here. It looks a little bit complicated, but actually it's quite easy to show that this coefficient here is always smaller than 1. And this is, again, using this property here of positivity, the fact that Carnot is always positive, so this is always positive, this is always positive. So this is, you see, this is the same as this. This is always positive, so this will be always smaller than 1. And therefore, my efficiency at maximum power will be always smaller than half of the Carnot efficiency. And the maximum, when do I reach this maximum half of Carnot efficiency? It's precisely in this tight coupling condition. Okay? So I'm sorry that I did, this is the missing link. It's not difficult, really, to show that the efficiency only depends on this ratio. You can rewrite the efficiency in terms of that. You replace this in that, and you will find this expression. And it's remarkable. We have a very general result, which depends only on this Onsager coefficient, and that tells us that efficiency at maximum power in the linear regime, it's crucial, we did this assumption here, is always smaller than half of the Carnot efficiency. And we reach this maximum in the tight coupling regime. Okay, that's the important message to keep in mind. So we have a universal in the sense that it's system independent, but not in the sense that it's far from equilibrium, because here we are in the linear regime close to equilibrium. But we have a universal result telling us that close to equilibrium, efficiency at maximum power is at best half of the Carnot efficiency, and it can be lower if we don't have this tight coupling condition. Now, it's difficult to go to make general statement beyond the linear regime. I will make specific statement on the model that we will look at, but general statements are difficult beyond linear regime. I will only mention that there are some phenomenological approaches that derived results which are of this form for the efficiency at maximum power. It relies on various approximative schemes that I have no time to go into now. And you see, it's more general than half of Carnot efficiency, but if you expand in terms of the Carnot efficiency, and the Carnot efficiency is related to the gradient, so expanding around the Carnot is like going a little bit beyond the linear regime, you again find that it's this half of the Carnot plus higher order correction. So this was obtained long ago. You see 57 people studying power plants and efficiency of nuclear power plants and stuff like that. They derived this. And they got this factor here plus higher order factor, so they got this general relation. We have specific cases where we can claim that this is also generic, but we need to put additional constraint, and for the details you should look at this paper here. But we showed that in cases where systems have certain symmetry property, which are related to the fact that if you switch the two baths, so you have a left and a right bath, and the current is antisymmetric with respect to this shift. So it's usually systems that are structured in terms of a hot and a cold reservoir on one side and on the other, not some more complicated connectivity. Then you can show that beyond, at the first nonlinear order, you can also you can understand why you have this 1/8 factor. But the main message here is beyond linear, in general, it's very difficult to say something universal, okay? But we will study specific model where we can really go far from equilibrium. And now I enter the application aspects. I will start with a very simple model for the thermoelectric effect. Okay, so what do we have here? We have a single level. Think of a quantum dot or a molecule where we can restrict ourselves to only one level. So when an electron goes in, it can only find a single level in which it can sit. For those of you who are not familiar with quantum dots, is when you confine very strongly a quantum system, think of a particle in a box, the quantum levels, the spacing between the quantum levels becomes bigger and bigger. So when the system is very small, you can basically, in certain regime, have a dynamic which only involves one level because the other levels are way too high or way too low. So you have a single level, and your electron can jump in this level or jump out of this level. When it goes in, it will acquire the energy epsilon. When it's out, energy will be 0. Okay, and that's the simplest model, a single level quantum dot here, which can be empty or filled. And I have two electronic leads. So this is a bath of electron. We usually assume free bath of electron. It's metal leads, so electrons move freely in these things, and they are always equilibrated because it's a very big system. And occasionally they can jump in and out from these metal leads to the quantum dot. It's a tunneling process. So this junction really look like, if you, in real experiments, you will have a little island here, very of semiconducting object, very small. It can be of the order of the nanometer, so that you can have only everything happening around one single quantum level. And here it's insulator, and here it's again metal, semiconducting. And so what you have is this electron here which are free, and occasionally they can tunnel into this level or get out or in this direction here. and here, okay? And in experiment, they can control the chemical potential of this lead and the temperature. Temperature is a little bit more tricky, actually, to control experimentally. Okay, so this is the kind of models. So in the stochastic description, now this is another story. I could give a whole talk on how to start from a microscopic Hamiltonian for these kinds of model and go to this very simple rate equation, which I didn't write down, but it's the same rate equation as before, P dot. But now I have only two levels. So I said I could do a whole theory to go to this, but it can be done, okay? And this theory will give me the local detail balance condition. So I guarantee you that the microscopic theory of this description can be done in certain limits, and that it satisfies the condition for having all this formalism here of stochastic thermodynamics that applies. Now, the point is that it's, of course, I did a microscopic theory, so I get more than only the ratio of the rates. I know exactly how the rate look like. These rates, so I said I have two levels, which correspond in the stochastic description, correspond to the level empty and the level filled. Okay? So this guy can be empty, so with or without an electron. So this means two levels. In quantum mechanics, we call this many-body levels, because in the many-body space, a level can be empty or filled. So these are two many-body states. And we have transition between this, and this rate give us the probability to make this jump. The probability to go from the empty level to the filled one is a coefficient times the Fermi distribution of the lead that makes the transition at the value of this level here. This means that we know that Fermi distribution is the equilibrium distribution of fermions, and electrons are fermions. So the rates are proportional to the probability to take one electron from the lead, and this is proportional to F, and bring it into the system. Now, the probability to go from the filled level to the empty one, it's 1 minus the Fermi, because this is the probability that I take my electron from here, and I find an empty spot in my lead. And the probability to have an empty spot is precisely 1 minus this Fermi. So you see, you can do a sophisticated theory, but at the end, you find something that is very intuitive. This is actually called Fermi golden rule rates. And it's related, probability to get in the system is related to the Fermi. To get out is 1 minus the Fermi. It will make really sense in terms of the stochastic description, because Fermi is when you need to take an electron and bring it into the system. 1 minus Fermi is when you need to find an empty spot for the electron in the lead. Okay? So these are the rates. And these coefficients will depend on the tunneling coefficients that you put in your microscopic Hamiltonian when you write Hamiltonian of the system, Hamiltonian of the two reservoirs, and some tunneling terms here in between. These tunneling terms will end up in these coefficients here. Okay, so this is the description. So we have the rates, and we can apply all the formalism that I described. So here, the heat from the right reservoir will take this form. Okay, the fact that I can relate everything in terms of a single current is related to this tight binding, tight coupling condition, because you remember heat was energy current minus mu times matter current. In this model, I have tight coupling, meaning I have proportionality between my heat and my matter current, because the only way to change the energy of my level is to bring an electron in my system. So that's what I meant when I said the carrier of heat is the matter current. So every time I bring a particle in, I bring an energy that is proportional, a factor epsilon times the current of particle in. Okay? So this model has tight coupling condition built in. And this is why I can express the heat only in terms of a single current. I don't have this difference of the heat and matter current, energy and matter current. I can express everything in terms of the particle current here, which is given by this. In this model, it's a 2x2 stochastic rate. You can find explicitly the stationary distribution, and you can calculate this current. It's a difference between the probability to get up and the probability to get down from the right reservoir. And since the right will be minus the left, this is really the unique current characterizing the flow of particles at steady state through your system. So I know heat. Work will be the sum of the heat from the right plus left reservoir. You can do that. You will find, again, this structure that we had, the difference in chemical potential times the current. You can define the efficiency, the ratio of the work output divided by the heat coming from the hot reservoir. Takes this form. You remember I said in the tight coupling, the efficiency is current independent. Indeed, again, we don't have an explicit dependence on the current here. And I have everything. So I know how to calculate everything. So I can really now calculate, for example, the efficiency at maximum power. I will not go into the detail, but this is to give you an idea of the derivation. It's convenient to use this variable XL and XR, which are the argument of the Fermi distribution. You write the work in terms of this variable. The efficiency in terms of this variable reads like that. And you look for the maximum work, power. Work per unit time is power. You maximize this work with respect to this XL and XR. You get a two system of equation. And you can write the solution of this system in the following form. You see, from one equation you get XL in terms of XR. You plug this in the other equation and you get this equation for XR. So this is almost solved, but you cannot explicitly write XR equals something because these functions cannot be inverted. So it's a transcendental equation. But it's very easy to find this solution on a computer. You simply find the zero of this function, right? So this is almost analytical. You can simply plot now these results. So I maximized power. Okay, I will find the XL and XR numerically corresponding to this power. Plug them in my definition of efficiency. And this is what I will get. This axis represents the efficiency at maximum power. And this is the Carnot efficiency. I use this again as a measure of the difference in temperature in my system. So it means that if the two temperatures are almost identical, I'm here. And this is the regime close to equilibrium because the gradient, if the two temperatures are almost the same, the gradient is small. And here I go further and further away from equilibrium. The difference here between the two temperatures is very high. And for each of these gradients, I plot the corresponding efficiency at max power, which is the efficiency where I put the XL and XR that I obtain from maximizing power. Okay? And this is the black line is the exact solution. So this is, for a simple model like that, you can really get it. And it's interesting because you recover at low gradients. You see the coefficient here is half of the Carnot efficiency. This was our prediction for the efficiency at max power, half of the Carnot efficiency. If we had tight coupling, since this system has tight coupling, it's not surprising that we get this half of the Carnot efficiency. We can show that we also get the higher order correction with respect to this Kurtzen-Alborn result that I showed you perturbatively. You can show that the first nonlinear correction is that one. But you see, further away from equilibrium, the Kurzon-Alborn result, which was obtained, as I said, using some phenomenological approximation, is not coinciding anymore with the exact result. The deviation, though, is not so bad, so this is quite remarkable. But far from equilibrium, the exact result is different. But what is nice in this model is that we can really get almost analytically, in the sense that I cannot explicitly isolate XR, but this is almost analytically, we can calculate the efficiency at maximum power. And here, it's a plot of the corresponding value of XL and XR, but this doesn't help you a lot. But what is interesting is that this is proportional to power, you see, up to some scaling coefficient. And you see, when you are close to equilibrium, in the region of small temperature gradients, power is very low. So to increase the value of your power at a given, of course, we maximize at a power at a given value of the gradient. But as you increase the gradient, the value of the max power increases also. So further away you go from equilibrium, the higher your power output. Okay, so this was the thermoelectric effect. We looked at how we can, out of equilibrium, generate this flux against the bias using this thermal gradient. And now I will finish with the photoelectric nanocells, which is making contact with the main topic of this conference. Again, it's a very simple model, but it contains nice things to discuss tight coupling, because we can interpolate between a tight coupling regime and a non-tight coupling regime. So here we have the following setup. We have the sun, and the sun is a thermal object. It's a black body, so it has thermal radiation. And photons are bosons, so the statistics of the sun is bosonic. And yeah, you should correct this. This is N. The Bose, so this is, you see I have Bose rates here, so this is not F, this is N. So the sun is a bath at equilibrium of bosonic particles, and this is why we will have rates containing this Bose distribution, while the leads here are electronic reservoirs, and electrons are fermions, so we will have the Fermi distribution appearing in some of these rates. I will go into the detail of the meaning of these rates, but I want to first say that we have Bose and Fermi rates here, because bosons are photons from the sun, Fermi are electrons from the lead. The sun is at a high temperature, of course. The leads are, we assume, on Earth, so much lower temperature. And we have electrons here sitting at a certain chemical potential, which is low. And here, electrons sitting at a higher chemical potential. So without help of the sun, of course, electrons would flow from this lead to this lead. But what we want to do now is use the energy coming from the sun to pump electrons from lower to higher chemical potential. Okay? And the way we do that is the following. So we have one quantum level, as before, that is only coupled interacting with this reservoir, and this other quantum level that is only interacting with this reservoir. Now, how do these two levels talk to each other? In the sense that if I put an electron here, I need a mechanism to bring it here, and this is precisely what the sun is going to do. So this bath generates this transition. And then once, so I can bring an electron from here to here, the sun brings it from here to here, and again, due to this reservoir, I can bring it from here to here, okay? In many body space, again, looks frightening as a word, but it's simple. we have 3 levels for this entire system here. One level corresponds to this and this level empty. Okay, no electron, neither here, neither here. A second level, which we label by R, is when this level is filled, but this one is empty. Okay? And then the third many-body level, when this one is filled and this one is empty. You may ask, and it's a relevant question, why don't you have the case where this and this is filled? I could, actually, but one way to argue that this might not be necessary is in this very confined system, electron-electron interactions are very strong. And so you can have sufficiently confined system so that the energy cost for double charging here and here is very high. And so you will never access it. And so you can basically neglect this fourth state. Okay? So is it clear, this 3-level structure? So these two guys empty, this and this empty, no electron in, is one level. One electron here, no electron here is another level. And no now I forgot in which sense. The third is the opposite, the switch. Okay? Again, we can write the rate equation for this system of 3 levels with the probability of occupying each of these 3 levels and the different rates associated to that. So let's take a few examples. For example, this rate will be the probability to go from the double empty level to L. L refers to this one filled. It means that I need to basically go from a situation where this one is empty to take one electron here and fill this level here. As before, how do I do this? I need to take an electron from here. So this will be proportional to the Fermi distribution of the left reservoir. And this is exactly what I have here, Fermi distribution of the left reservoir and some coefficient. Let's take another, a little bit more involved, which contains 2 processes. The one going from L to R, so going from this level filled and this one empty to this one empty and this one filled. Okay, so this transition. Well, here, let's first look at this one, because this one, sometimes I will neglect it and sometimes not. So let's first describe this one. This is the Bose distribution due to the sun, because the bath that will give me the energy to do this transition is the sun. And so I need to take a boson, which is a photon from the sun, to induce this transition. So I have the Bose distribution at the difference of this energy. And this is something else that I didn't put in these notes. You should write it down. Eg, the gap energy, is the difference between ER and EL. Okay? So this is the Bose distribution. I need a photon which has precisely that difference in energy to make this transition. Now, what is this other term? I assume that I could have other bosonic particles, and you might know that phonons are boson also. So these are vibrational effects, perturbation in a sense. So I could assume that this transition could also be due to some bosonic effect on Earth at the temperature T, which is the temperature of the Earth. And so this Bose distribution here will be at the temperature T, while this one is at the temperature Ts. Okay? And this should be clear here. Yeah. Xg as T and Xs as Ts here. Okay? And the other rates, of course, also here, to go in the opposite direction, so if you take one from the sun, it will be Bose. If you want to bring out one and send it back, this will be 1 plus n. Okay? This is emission. We always have the two processes going in the two directions. And same for the Fermi rates. Fermi and 1 minus Fermi, always to take in and to take out. Okay? So this describes with this set of rates, this master equation. I have the dynamics. I can again construct the thermodynamic description. Calculate the various fluxes. So this flux is the net flux of electrons crossing the system. Gs is the flux of photons coming from the sun. And this flux, Nr, stands for non-radiative. It's this phonon parasitic effects that I may or may not include. So it's, you see, the total flux, in case I have no non-radiative effects, will be the same as the flux going from the sun. This is clear from here, because the flux at which I can bring electron from here to here, if the only way to make this transition is to bring photons from the sun, these rates will be proportional to these rates, because I have to have photons from the sun to go from here to here. So in absence of these non-radiative effects, the two fluxes are the same. But in presence of this non-radiative flux, I have two fluxes that can make these transitions. And so the global flux is the sum of the photon flux and this parasitic bosonic flux coming from phonons. I can write the heat associated to each of the reservoirs. In general, I have 4 reservoirs. I have the 2 leads, left-right leads. I have the sun, which is the 3rd lead, and this other bosonic reservoir at temperature T, the non-radiative one, which is Q and R. So I can write entropy production will be the sum of each of these heat divided by their respective temperature. Left and right lead and the non-radiative phonon reservoir are all at temperature T. The sun is at temperature Ts. So I can again rewrite this as a flux force relation, where the force will be given by the thermal gradient for the U, and the second force is given by the Fermi, the difference in the chemical potential between the left and the right lead. The power, we are at steady state, so the power is the sum, minus work is the sum of all the heat because energy is conserved. So we can write this explicitly. And we again have this form that the power is the flux, the matter flux, as I said, the flux crossing the system, bringing electron from lower to higher chemical potential multiplied by this difference. So we have all the quantities to make the thermodynamic description. And once again, efficiency will be the power output divided by the heat from the hot reservoir. The hot reservoir here is the sun. So I can write it down explicitly. Now, okay, this is a good way to show what I couldn't show before. In general, I have the ratio of currents appearing here. And as I said, if I have this non-radiative parasitic effect from phonon that is also causing this transition between left and right levels, these two are different, and so this ratio is not 1. And so my efficiency will depend on the current. But if I switch off this non-radiative effect, I suppose that I can neglect this phonons effect. This, as we showed, is equal to this. And these two things drop, and my efficiency becomes current independent. This will be interesting now for the numerical result. It's a little bit more complicated, this model, so you cannot do everything analytically, but go quite far, and the rest has to be done numerically. I will start describing, so I again calculate maximum power with respect to the various parameters that I have. For a given value of the thermal gradient, I fix the thermal gradient and I maximize power with respect to these other parameters. And here I assume for a second that the non-radiative effects are off. So I am in this tight coupling regime where the fluxes are proportional. And you see, I get something which is quite similar to what I showed you before. So this is efficiency at maximum power, should be also here. The axis here goes from 0 to 1. It disappeared in the thing, but this is 0, this is 1, the Carnot. So for a given value of the gradient, this is the value of the efficiency at maximum power. This is the exact result for different sets of gammas. The gammas were these coefficients telling me how strong I couple to the bath. The message here is that for different choices, you see that my efficiency at maximum power doesn't change a lot. So these are not really relevant. Making an asymmetry between the coupling of these levels, between the different levels, is not very important. So playing with this, in the tight coupling regime, you stay very close to the same result. And again, we get that close to equilibrium, we get half of Carnot efficiency in this case. But further away, we get something different. And here, this is again this Kurzon-Alborn result, which is not the exact one, but gives a reasonably good idea of what is going on. Now, and this is the final important message, I turn on this non-radiative effect. So I lose this tight coupling condition that I mentioned to you. So now my efficiency is flux dependent. I don't have that this ratio disappear and is 1. And look at how my efficiency at max power decreases. I turn them on very weakly. You see a factor 10 compared to the typical interacting strengths with the other bath. Still, I have a big drop in my efficiency. If I couple it in the same order of magnitude with these non-radiative effects as the other processes with the other bath, I get a major drop. And you see, even close to equilibrium, I am below half of this Carnot efficiency as we predicted from the linear response analysis. So in the linear regime, also we are much below. We can get higher here, but we are even out of equilibrium. We remain very far from what we can reach in the tight coupling regime. So the message is that this tight coupling regime has a lot of interesting features, not only at equilibrium where you can have gradients but still, well, be at equilibrium but having gradients, but also when you go out of equilibrium, it's usually the best way to reach the highest efficiency is to try to get as close as possible to this tight coupling condition. And the universal results can be only showed close to equilibrium, as I did in the linear regime. Beyond that, one has to look at specific model to really be able to say something. Okay, I think I will stop here. I already went 5 minutes, and I will skip the last part on the time-dependent devices. Thank you.